Okay, we'll wait a couple more minutes to see if more folks shows up today. Okay, so we have about 15 people. Okay, so a little bit change of plans, I guess, on what we'll cover today. The rest of this following, so the topic will be going on is actually covering inequality constraints. But that's a sort of quite involved subject. There's a lot of details with that. So if we only have half the class here today, then that may create some issues down the line. Sort of makes the next homework will be difficult if you don't come to the class today. So I guess today we'll do a little bit change of topic. So we'll do a review of where we are. Then we'll switch to sort of this balancing load and generation. So we'll do the next class first, then come back to inequality constraints. Okay, so hopefully more people will be here next Monday when we cover inequality constraints. All right, so does that sound good to folks? Okay, yeah, so I'll do a little bit of switch, right? I guess it's understandable, half the class is not here, but we cover inequality constraints. That's a hard topic. It's a sort of hard class to learn, right? Without the chance to ask questions, you're just listening to a recording. So let's do a review, then we'll switch topics a little bit. We'll look at sort of a more, a less technical section of the class, I guess. Then, if we finish early today, we'll finish early for Thanksgiving today. So as a recap, we've been looking at the problems basically with equality constraints. Okay, so we've been looking at problem like this, mean x1, let's say I have x and variables, subject to this kind of equality constraints. And from last class, what we covered was basically that there's a very mechanical way of solving this problem. There's a quite mechanical way of doing it. Basically, you form the Lagrangian. You form the Lagrangian with Lagrange multipliers. Okay, get a bunch of Lagrange multipliers. And basically, then we can think of this as an unconstrained problem, right? So then we're going to mean over the Lagrangian. And this mean is over both x and lambda. So this is a function of both x and lambda, both over the so-called primal variables x and the multipliers lambda. Then if you do this mean, what we have to solve is basically a system of equations. Right, so we solve this system of equations. And for this class, what will always happen is f is quadratic. F is quadratic. These are omega I are linear. Okay, so this is a linear system. Okay, this is a linear system. So once you do this way, you follow this procedure, you get a linear system. Then once you get a linear system, then we can use, say, for example, computer to very easily solve this. Okay, so we have a quadratic constraint, we have quadratic cost function, we have linear constraints. So once you do the partial derivatives, you actually end up with a linear system. It's always a right dimension, so you can always solve for all the x and lambdas. Okay, so it's quite simple, just by the setup in the class, okay, by how the class is set up. So if you look at inequality constraints, right? So we don't have to always have equality constraints. There are always inequality constraints associated with the generators, for example, right? So if you look at economic dispatch, there's always inequality constraints because a generator cannot generate infinite amount of power. So if you look at a typical problem, what we have is mean something like, say, x2 subject to, this is a low balance equation, right? So this is sort of the equation we had before, but you also have upper and lower bound, right? We have this upper and lower bound. Because every generator has a minimum and maximum output level. So once you have inequality constraint, then the problem is not so nice anymore, right? It's not you cannot just form Lagrangian, go differentiate, and solve a linear system equations. It's no longer so simple. So once you have inequality constraint, it's actually a little bit tricky to solve this problem because you have to figure out, right? Is the inequality constraint holding at one upper lower bound? Is that not holding? Can we ignore the inequality constraints? So this is a little bit more complicated. Okay, so it turns out there is a way to solve this. But I think, as not everybody's here in the class today, and it's the day before Thanksgiving, so we cover this. Probably not many people will remember by the time next week comes along. We do this very technical stuff today. So let's, keep this in mind, right? So when we come back next week, we'll look at these problems. Today we'll cover a little bit sort of a less technical topic. Okay, we'll cover the topics. So we'll switch gears. We'll cover topics of balancing load and generation. Okay, so we'll go to balancing load and generation. All right. So we'll do a skirt gear. We'll come back to the optimization with inequality constraint later. We'll come back to this optimization problem later. We'll cover today. We'll look at the balancing generation and load. Okay, so balancing generation and load basically comes from the following observation, or not coming from the following fact, right? So you can think of basically what does solving OPF do, right? So what solving OPF, solving power flow does, solving economic dispatch, what it does is says, we're going to solve economic dispatch, right? So this says give a load, find the optimal generation, which often means the least cost generation. So we solve this problem. Right? So this is the optimizing the resource allocation in the system, right? So my generators are my resources. as allocate them, satisfy demand in an optimal way. So this is a very common networking problem, resource allocation. But if you think about this in the power system, let's say in a grid, how often is this problem solved? Anybody have a feeling? Right? So how often do we solve this problem? Is it once per day, once a month, once per hour? How often do you think we solve this? I have a guess. That's your system operator, right? You have to balance. Right, so this chat says hourly. So this problem is basically solved hourly, quite common, or let's say 15 minutes. Load office is trade energy, right? So basically this is solved as a resource allocation problem, hourly or 15 minutes or 5 minutes or a day, this kind of intervals. Okay, so solved at discrete intervals during the day. Okay, solved at discrete intervals during the day. So let's say even if you solve it every 15 minutes, right? What if the load changes within this interval? Okay, so when we solve economic dispatch, when we dispatch the generators, we're solving for snapshotting time. Right? We'll say load is 10 megawatt, load is 15 megawatt, and things like this. But loads are continuous changing, right? We flick on the light all the time, right? We're gonna flick on a light, we're gonna turn on a computer, we're gonna charge a phone, we're gonna disconnect the phone, things like this. The load is actually not something that changes in discrete time scales, right? Load changes at every, continuously, basically. At every microsecond, the total load is different in the system. Okay? So the question is, if a load is different at every time scale in the system, at the changes continuously, then our goal is we want to understand how is actually the system actually balanced. Okay? How is the system actually balanced at how is the system balanced at all these continuous time scales? So this is one goal, right? So we're solving this economic dispatch in every snapshot in time. But actually, what we're doing is we have continuous changing load. So between this, let's say 5-minute intervals, the system has to do something. Okay, you flip, you plug in your computer, you accept your computer to be charged, right, to get power. So we have to continuously adapt. So we're going to look at several things. One is, load actually changes continuously. So we have the continuously changing load, right? So one is we're going to look at what happens when the load changes continuously. How do we think about this problem? Okay, how do we think about this problem? Another thing we're going to think of is we have power flow in the system. Is how do I think about intuitive things like voltage? Okay, so another goal is to think about voltage, line flows in terms of power. Okay, right? So we're solving this load. We're solving this resource allocation problem, generator to load. In that, if you remember the economic dispatch problem, we did not really talk about voltage. Okay? We never talk about voltage. Just a generator has this much generation and goes out to the load. Our goal here is really to get a sort of intuitive understanding. If I solve this problem, what happens in the intervals in between 5 minutes? And how does this impact the voltage and line flow and losses in the system? Okay, so that's our goal. And there is a way to handle it in a very technical manner. For example, if you combine the economic dispatch with the power flow problem you guys are solving for this homework, if you combine both together, we can actually, have a very optimization or mathematical way of dealing with such problems. But think of the trouble you're having now, writing the homework, doing the homework. Think of what happens if you want to optimize on top of it. Okay? So that's a hard thing to do. And that may not give you, intuitively at that point is basically just cranking through using computer, right? So here we want some intuitive idea, right? What happens in the 5 minutes, what happens, how does the voltage change, things like this. Okay, this is a goal we're trying to cover, right? So there is a way to do all this very rigorously, but that's a little bit beyond this course. Okay, so today we're gonna do a more in a sort of hand waving, but hopefully enough physical intuition, okay, to get us to where we're going. All right. Any questions with the goal of this? Any questions about power balance at this high level? Okay, all right, so let's look at this. All right, so if you look at the energy delivery system, right, this is a block diagram level of energy delivery system. Then basically we have, 4 things that happens, or four things that happens. And these are the power injected into a system, right? How much power we put into the system, how much power we extract, and there are some storage going on, and there are some losses that happen in the system. So basically what the transmission system does is keeps these 4 things balanced. Okay, these 4 things are always balanced. Okay, the energy input is equal to the energy output plus the loss plus the energy that's stored in the system. Okay, there's some energy getting sloshed around in the system. So we always have this conservation of energy, right? So if you look at the conservation of energy, what we always have is the energy input, okay, the total energy into it, equal to the output, how much will I withdraw from the system, equal to the loss in the system. So you can think of this as a thermal loss in the system, plus the stored energy in the system, plus the stored energy in the system. Okay, so this is what we always have. So one thing to keep in mind with this number notation is this is positive, right? So the loss is almost always positive, at least for active power, that we're losing energy. This can be positive or negative. Okay, this depends on if you're, either you're putting energy into storage or you're withdrawing energy out of storage. So this sign can change. Okay, so sometimes you're putting energy into it, storage, sometimes you're withdrawing energy out of storage. So just at the high level, before we go into sort of more math, what kind of storage do we have in the system? That's not batteries. Right? So battery electric, so I said batteries as a, explicit storage, but what other storage do we have? Capacitors, not really. For the, so chat, capacitor is one possibility, but in the power system, capacitor stores very little active energy, right? So we have capacitor most for reactive storage. Inertia is more the storage of active energy, right? So for all the spinning machines, they basically all have inertia. So this is a form of storage that comes in between, let's say within the 5-minute interval or within a minute interval. As you have this big spinning generators that anytime you have this sort of mechanical inertia, it stores energy. And also this on the generator part. On the load, does any of the load store energy? Right, so we have storage, right? So storage is of generator. So this is mechanical inertia, basically. Does any of load have mechanical inertia? Any types of load have this? So think of the things in your home. What actually spins? You look at all the things in your home that withdraw electricity, right? So your light does not store energy. Your computers, they don't store energy. What does actually store energy in your home?
Washing utilities.
Right. So your washing machine stores energy. Your dryer stores energy. Your refrigerator, the motor, stores energy. Right. So all of these are the sort of mechanical storage we have. Okay? So load motors, basically. So whenever you have a motor that spins around, that is a form of energy storage in the system, right? Because it can spin a little bit faster, a little bit slower. It doesn't stop, when the power goes out, things like this. So these are actually the storage units. And this is important. The power system does not work without this, at least this sort of little amount of energy. Okay? That does not store this much energy. So this is the form it has to work. Hot water tank. So can you clarify what does hot water tank mean here? For the folks in the chat who's saying, oh, heat is energy. No, that's not the form that's useful for the power system in a minute-to-minute balancing. Okay, so your hot water tank does store energy. As you know, it doesn't have to be heated up constantly, but that's not how the power system deal with it right now. Okay, so you can use hot water tank as a form of demand response, but it's a little bit removed from the energy storage in the sense we're going to think about. Or basically, you're going to think about spinning things that can spin a little bit faster, a little bit slower when there's a little bit power imbalance in the system. That's how we're going to think about it. So let's look at the energy storage in a more mathematical form, right? In a mathematical form. So we often say a system works in steady state, right? So right now you can think of the power system right now for Seattle, for example, working at steady state. So steady state means that the rate of energy consumption is energy conversion is constant. Okay, so this means the rate of energy is constant, right? So there's energy in equals to energy out plus loss plus storage. So power, right, is d dt. Okay, power is d dt, and this means that now this is some constant. Right? Oh, sorry. No, sorry. This means the power is d dt, so the net power equals to 0, right? So net energy is a constant, net power is 0. So equivalently, E is the changing power. So if you think of this way, being in steady state, that this is 0, there's no net gain of energy, there's no net loss of energy. Okay, so this is our power. So then this is basically a steady state as an approximation, basically. Okay, so sort of engineering approximation we have. Nothing is really steady state, right? So the power is not always exactly 0. The net power exchange is not always exactly 0, but this is sort of a useful notion to have, right? Steady state is a useful notion to have. It basically gives us a point to start doing analysis. Okay, this is the reason we talk about steady state. So if you look at steady state, right? If you look at steady state, so what does it mean, right? So you look at these 3 terms. So in steady state, let's look at the power flow in all of this, right? So at steady state, we have this is P in, this is a constant. Okay? This is a constant because we're not, changing the rate of energy input into the system, for example. Similarly, this is a constant. The loss is a constant because none of the energy conversions change. So what about stored? So if I claim my system is in steady state, meaning there's nothing's changing in the system basically, what is the time derivative of the energy stored in the system? So every other thing is a constant, right? So for every other things, is some constant power. But what for storage, right? For storage, it actually has to be zero. Okay, it cannot be a constant. This has to be zero for energy storage. Okay, because the reason is, if this is a constant but not zero, we're actually always putting some energy into storage or always withdrawing from storage. But that's not steady state. Okay, that's not steady state. Okay, so for steady state, here we mean as we have P in, basically equals P out plus P loss. Okay, so this is for our steady state. We have this kind of power balance. And in a steady state, we're not, putting in net energy into a storage, right? So if you think of storage being the spinning of a generator, it's not going to always accelerate or decelerate. Even if the generator changes a little bit, the frequency or the rate of rotation will increase a little bit, will decrease, so we'll always hover around a steady state. Right? So that means at least in the average sense, the net change in energy storage should be zero. Right? Otherwise, the system, is not sustainable if the system has a non-zero rate of storage. Right? So on average sense, that the storage should work out to be zero. Okay? So this is a steady state situation. Right? We don't have energy storage, and the power in equals power out plus the power loss in the system. Okay? So this system operating correctly, or at the first approximation for steady state, this is the case. We have a power balance. But of course, the system does not have to operate at steady state, right? Anytime we flick on a light, for example, this is we change we charge or discharge something, we add a load, subtract a load into a system, it's not in steady state. Okay? When it's not in steady state, basically the power input is not equal to the power output plus the loss. Okay, so there's a slight imbalance between the amount of power you put in and then the amount of power you get out of it. So that's why this energy storage is important. Okay, that's why this energy storage is important. Without a little bit of storage, the system cannot work. Okay, because we cannot have power balance in a non-steady state. So to always have power balance, the system, we have to have storage in the system. Okay? So you may hear, people say, oh, the existing power system, we don't have storage, we need to put in batteries, things like this. It's not exactly true that today's power systems do not have storage. Okay, we always have some sort of storage to make this work. So this is analogous to, let's say you're surfing on the internet, you have a buffer, right? So for internet to work, you need some sort of buffer. For power system to work, you need at least a little bit of storage for the power system to work. All right, so we're going to look at where does the storage come from. Well, this, right now for the existing system, the storage comes from basically we have rotating generators, we have synchronous generators. This may change. We have a lot of renewables coming to the system, but for now, at least, this mostly comes from the generators that we have, spinning generators we have. Right, so if you look at this rotating generator as power input, basically you have a primary energy source. Thinking about from hydro. This comes from water flow in hydro. Turns a shaft and then goes into electric energy. Okay. So this is the form of energy conversion we have in these generators. So let's look at, do a little bit more calculation to look at, what are the storage, right? So if you look at this mechanical system, basically this mechanical system together have some inertia J, right? So there's the turbine, shaft, and the generator. These are all spinning, big spinning machines. They have, so together has some inertia J. Okay? You know how we have inertia, and this rotates at angular speed, omega, right? Radians per second, let's say. Then what is the stored energy? If I have inertia J, and I'm rotating at angular speed omega, what is the mechanical energy in the system? Somebody remember the formula? For a rotating system, if an inertia is J, the angular speed is omega.
1/2 J omega squared.
Right, so this is the mechanical energy. This has is 1/2 J omega squared. Right? So this is the mechanical energy that we have in the system. So basically, this is this J being non-zero gives us some inertia, and this gives us a some storage in form of energy storage. Okay? So if you look at the generator, the generator does have some sort of magnetic components, right? For example, the generator has an inductor. When we do a generator model, has an inductor inside of it that can perform, that gives us some little bit energy storage. You know, it may have a shunt capacitor, things like this. But normally for generators, this J is large, you know, greater, much larger than any sort of the magnetic components. Right. So really, most of the energy exchange happens, you know, is from the mechanical inertia, not so much the magnetics in the generator. Right? So the inductor, even though it's storage energy, for us is not important. It's much smaller than the actually mechanical spinning turbine, for example, in the generator. Okay? This will change, right? So this is different if you look at the solar cell. If you look at solar cell, there's no J. J is 0. There's nothing spinning there. I mean, for a solar cell, for example, all the energy storage is in the inductor and capacitor in the solar cell. That is very different than this form, but for now, we'll cover the traditional synchronous generators. We ignore capacitor inductors because we have a J. Whenever you get to something where there's no mechanical inertia, you have to start to worry about the capacitor inductor storage. But here we just ignore that. Okay? J is much larger than that. So if you look at the simplified model of this, then if you look at a simplified model, basically what we have is this is the primary energy form, this is the loss, this is the energy that goes into the loss, and we have some sort of energy being stored based on this form, J omega squared, okay, J ms squared. And this omega you can think of as the deviation from 60 hertz, or from times 60, right? So if the omega is 60 hertz, you can think of that steady state. Nothing is being stored because that is the nominal operating condition. So that gets into the system. But whenever the frequency goes away from 60 hertz, that means there's a little bit of storage in the system, right? That's the sort of the net change in energy being stored in the generator. Okay, so right, so if you again look at the simplified storage, so if we can look at this as Okay, so let's look at this model. So for basically what we want to do is we want to say this loss, this is small, and we're going to ignore the loss. We're going to ignore the loss for now. And it doesn't change any of the argument. It's just one more extra term we have to write. So we're going to assume that's 0 and not worry about the loss. Okay. So, and if omega is 60 hertz, not 60 hertz, 2 pi times 60, there's sort of no net energy, no energy stored. Right? So if you're operating at steady state, 60 hertz, this is actually not energy exchange. Okay? The interesting thing comes from what happens when you are not operating at 60 hertz, or what happens when you're not operating at steady state. So let's look at an operation that's not at steady state. So let's look at, okay, so what happens, for example, when the load suddenly increases? Okay, so when I say what happens when the load increases, so when the load increases, basically this as the electric power, the output has to increase. The electric power increases. But the primary power, for example, cannot change fast. So basically, we have an imbalance between the primary source of the power input into the generator of the power plant and the amount of power the load is asking, right? So there's an imbalance. Then what happens is the stored energy decreases. Okay, the stored energy decreases, right? This stored energy decreases because energy is now flowing from the storage to the load. Okay? This decreases. If this decreases, what happens to the frequency? What happens to the rotation speed in the system? So if E stored, okay, so if the E goes down because we're pumping out energy, what happens to the frequency, right? Frequency has to reduce, right? So the frequency has to go down, then this sort of implies that omega decreases. Right? So it's spinning a little bit slower because this means that the energy is being pumped out. Okay? This energy goes out to the system, right? So the frequency is actually a good monitor. The frequency is a very good indicator of the total net imbalance in the system. So if you actually attach an oscilloscope to your own socket, right, to any of the socket you have, you actually, if you view the frequency, it's actually always going up and down around 60. It's actually always going up and down, because it's responding to this sort of continuous changing load in the system. So the frequency, although it's nominally 60 hertz, it's actually never exactly 60 hertz. Always sort of drifts around a little bit 60 hertz. It's always drifting. And that's actually how we figure out whether the system is, stable or not. The system is operating well in a good condition or bad condition, as we look at the frequency. So if you look at the primary power control, primary power. So what's preventing the primary power from changing very fast? Right? Why not just adapt the primary source to always match the load? Right? So what's preventing primary power from changing fast? It's a good idea to have a time scale of what fast means and what is slow. Right? When we say it cannot change very fast, how fast is fast?
Takes a lot of energy to speed it up and slow it down.
It's not so much energy to speed up and slow down. It's more of the amount of time you need to change it, right? So let's say you're operating a hydro plant, okay? What is normally sort of the time constant of change in a hydropower plant, if you think about it. Like how fast can the hydropower plant change its output? And so how does hydro actually change its output? How does it change the primary power output? Any ideas? Let's say you're operating hydro. How do we change the power input? Right, you have to change the flow rate. Basically, you have a governor, you have a valve, you have to open and close. That is its own mechanical process, right? And that takes a couple of seconds actually to change that. Okay, takes a couple of seconds. If you're operating a nuclear power plant, for example, you have this sort of rods. You have to extract them or put them up and down. That takes a couple of seconds. You have a coal-fired power plant. You basically have to pump the amount of coal that goes into steam, and the steam changes the primary power input. And that takes longer. That takes at least a couple of minutes. Okay, so meaning cannot change fast. Meaning cannot change in a few seconds, for example. But within this few seconds, you have to always have a power balance. So that's why you extract this amount of mechanical energy from the rotation. Okay, so cannot change fast, that doesn't mean it never changes. It means, cannot respond in a second to second time scale. And within a few seconds or a minute, we have to get the energy from somewhere. And we get that from the storage, right? From the stored kinetic energy we have in the system. So it's a similar story, right? If the load decreases, the load can go both up and down, right, in the same time. Right, at the same time. So it doesn't have to always increase. So it can decrease at times. So what happens is, well, to put energy into storage. Okay, so we have to put it in. So this means that omega increases. Okay, to increase the frequency. Right, so if frequency is higher than 60, means I have more generation than load. If the frequency is lower than 60, means I have more load than generation. Okay. This is what we have. But of course, our goal is to keep the frequency constant, right? We need to keep the frequency constant. We cannot, let the frequency drift, right? So our goal is always to, make, if the frequency goes away from 60 hertz, we want to come back to 60 hertz. And this is why, if you look at all the generators, most of the generators, what we have is we have a feedback control. We have a feedback control loop in the generators to make sure the frequency is constant. So we want to keep the frequency at least tracking the 60 hertz. Okay. So if you look at most turbines, the turbine works like this. So this is my turbine. Basically, I have what we have is we have a valve on the turbine. And there's some valve in the turbine. This turbine goes to the generator. This is the electric energy. So what we do is we actually look at the actual energy being measured. And we're going to subtract away from the reference, for example, 2 pi 60. This produces a delta in the frequency. And this goes basically into a control block. And the changes, you can think of the valve opening and closing into the turbine. Okay, so this is a regulator. Okay, this is a regulator. And this regulator basically adjusts so such that we always track the frequency, right? We track the frequency. So if you look at the regulator control law, okay, so it basically does the form of feedback control. There's a form of feedback control. So if you're gonna write this feedback control law, can you guys suggest some idea of the feedback control we're gonna use? Right, so what form does this law take? We're doing feedback control. Right, so this mostly looks like some version of minus k delta omega, right? So this says if omega is high, so this means that if delta omega is larger than 0, we're going to close valves, or if delta omega is less than 0, we're going to open the valve, right? So this sort of negative feedback control, meaning that so we have negative feedback control, we can always keep the system operating sort of close to steady state. Any questions about this? Here's the feedback control. So if you actually, so for anybody who's actually working with a generator, the regular control is not so simple. Okay, if you're actually working with a generator, this is actually a fairly high order feedback controller. So this is its own special area of how do you design a regulator control for a generator, because a generator is normally some nonlinear system. So it's not so simple. You slap a negative feedback on the generator, and this thing always works, right? So normally this is sort of high order controller. You design this still mostly in frequency domain. So for the people who take in control systems, remember Laplace transform, and we are going to design this. Is the process always automated? Right. There's no people in the loop. There's no humans in the loop in this. So you code this into the regulator. You have a microcontroller basically running this regulator, and it's a automatic feedback control. So there's no humans looking at this. There's nothing. Yeah. So for power systems, there's nobody looking at it. It's not worth the effort to have somebody looking at this regulator. There's nobody tuning this by hand. And you basically just let this go, and this will keep the frequency roughly constant. I think Milo is saying the Navy needs to upgrade their system. Right, so there's a very different if you say you're in a Navy ship versus a generator. Okay, so a generator basically have like 2 people inside of it, just looking at it, not as a Navy ship, right? So I think for the Navy, it's really saving costs is probably not the first priority. Although for generators, saving costs is the first priority. So this is all automated. There's nobody sitting there. Actually, if you go to a lot of generators, they actually don't remember what exactly the governor, the regulator is set at. Okay, so, for example, there's very old generators that they don't use electronics to do control. As a hardware sort of mechanical controller, actually. And somebody designed that, and it is what it is for the mechanical controller. And to this, for a lot of generators, we actually don't know what, we can't write down, for example, the constant K. We don't know what it is. It's just something that in the feedback loop. For a lot of newer generators, it is a microcontroller. At least it's programmable, you can program it, but it's not programmed very often. It's, comes out of the factory, and somebody builds a generator, they just have some setting and it's sitting there. And if you look at Idaho National Lab, basically Idaho National Lab, in the past year, went to hack this regulator and show how you can blow up a generator by hacking this regulator. Basically, they basically went in and it's a diesel generator. It's actually connected. It's connected to the internet so you can change the control law. You can program this, but then they went in and hacked it, and basically blew up a generator. And so there's some cybersecurity concerns, right? So yeah, so a Navy, also may have this, right? Sometimes you want the humans to look at. So there are actually a lot of so this is basically a jupe, right? So for the people who work in submarines and in ships, this is called a regulator with jupe. This K is a jupe constant. So basically, as a negative feedback controller, droop means as the frequency changes, the power will change. This is used quite often in a lot of systems. Okay. So yeah, so let's take a break now, I guess. We'll come back. We'll keep looking at this sort of generator droop, this sort of frequency control. Right? This is an important application in a lot of systems. Yeah, so let's take a break until 10:30, and then we'll continue with the regulator control. We'll look at the frequency control in the system. And for the folks who's serving the military, actually, ECE has a good tradition. So if you've taken a course from Rich Christie, for example, or you know Rich Christie was a submarine commander, actually. And his job was, he was a nuclear submarine commander, and I think his job was also to look at this power systems submarine. So he's still teaching courses, Sometimes he'll tell you a story, if you don't operate things correctly, what can go wrong in a submarine, which is quite fun. So you got to take a course from him. You can ask him of those kind of stories. You can tell. Okay, so yeah, if you have a question about homework, please ask. Otherwise, we'll come back at 10:30. Yeah, go ahead.
So you see the regulator is like the minus k times delta omega.
Yeah.
So
okay, sorry, I think I missed a question.
Oh, so the minus k times the delta omega here.
Yeah.
So what's this mean by regulator here?
So this is a feedback control, right? So the regulator controls basically how much, you can think of how much fluid that's being steamed, going into the turbine. So this is sort of the size of the valve, the opening on the valve in the regulator.
Okay.
So if you take, this is just the feedback control. This is a controller in feedback control.
So the delta omega is the difference, like the turbo omega minus like the turbo of the generator. I mean the delta omega of the generator.
So the omega reference is a hard code number, right? So that's
2 pi 16.
This is hard coded.
So how we calculate the delta omega?
Oh, you measure, right? So you have a turbine that's spinning at some rate. You have a sensor, you measure this rate of the spin.
Oh, so
the turbine.
The turbine minus the 60 hertz.
Yeah.
And if the larger, so close, okay. And also I have a question for the Jacobian matrix in the homework. So for the generator, we have the, so for the generator, we know the V set is just voltage. For the, and so only need to calculate the, but for the generator, we don't know the theta is angle. And for the demand, we don't know the voltage and the angle. So when we build the Jacobian matrix, do we still need to calculate from the P? We don't have to do the P1 because P1 is slack path. We have to do from the P2 to the P12 and the Q2 to the Q12. Right?
What's the question?
So for the Jacobian matrix, so for the how many rows do I build?
Okay, so that's a good question. So Jacobian matrix is a square, right? So the number of rows equals the number of columns. So let's look at this. All right, so this is homework. So I have a Jacobian, right? So what's the size of Jacobian? Okay, so it's still easier to think of the Jacobian in terms of blocks, but just remember the blocks are not of the same size. Okay, so we're gonna still think of this as blocks. Okay, so this is the blocks. So let's look at the block of this dp theta. What's the size of this block?
So I think for the theta we count from the 2 to 12. So bus 2 to bus 12. So which means 11 in the column. So
okay, so this is 11 by 11, right?
Yes. So the P is from P2 to P11, and theta is from C2 to C11. Okay.
Theta 2 to theta 12, right? 12 buses.
Yes.
So it's 11 by 11, right? So for every, we have P for every bus that's not a slack. We don't know the theta for every bus that's not a slack. So this is 11 by 11. What is this dimension then?
So I think the voltage, because we only care about the demand voltage from the bus 4 to bus 9 and the bus 11. So which means 7 bus.
Okay. So we have 11 active power, right? So we have basically 7, right? So we have, so to write out this a little bit more, the first row is dp1, dv4, right? Right. So I forgot exactly. Yeah. So this is 7 of them, right? There's 7 of these things, 7 voltages. So this is 11 by 7, right? 11 by 7.
Sure.
Right? So 11 active powers. There are 7 voltage variables, so 11 by 7.
Yeah.
How about dq d theta? What is this?
So the theta is still from the 2 to 12, and the Q is from the 2 to 12. So still be the 11 by 11.
Is Q from 2 to 12? For a PV bus, do you know what the Q is?
For the PV bus, so means generator.
Generator?
We don't know the Q, do we?
We don't know the Q, right? So Q is not a, Q doesn't enter into the generator bus.
Oh, so you mean for the generator, so there's no Q?
You can ignore the Q, right? There's some Q, but you don't know the value of the Q, so you can ignore Q for this calculation.
What do you mean by ignore the Q? Like the generator only generates the active power.
No. Generator generates both active and reactive power.
Yes.
Right. So you ignore it. So there's no, so Q is not 0, definitely. Okay, Q is definitely not 0.
Yeah.
It also doesn't mean there's no Q. There's always some Q within a generator. What I mean is you don't know the value of the Q, right? At the beginning of the problem. The active power from the generator is given, right? We know the number.
What's the active power from the given? Because the generator will
Column B, right? Column B. That's the active power given to you for a PV bus.
But the column C has the reactive power. And also,
right, but for a PV bus, we're not, it's not, the reactive power is not set in the beginning, right?
Oh, the PV is only P and V. Okay.
P and V, right? P and V. The reactive power is not set.
Yeah.
So how many Qs do we have? We only have the number of Qs for the load buses, right? For the PQ buses.
7 times 11.
7, right? So this is 7 times 11. dq dv, this is
7 times
7 by 7, right? So if you look at this whole matrix, this is 11 by 7. This is, sorry, 11 by 11. This is 11 by 7. 7 by 11, 7 by 7. Okay. So together, this is 18 rows and 18 columns.
Okay, 18 column here. And that's a Jacobian matrix.
That's a Jacobian matrix. Yeah.
So when we build a mismatch function, a mismatch equation, how many mismatch equations do we need to do?
So if the Jacobian is 18 by 18, how many mismatch equations can you have?
18.
18, right? So you're going to multiply the universal Jacobian onto that mismatch.
So we do the mismatch equation from the P2 to P12, and the Q is just the Q4 to Q9 and the Q11, because
yes.
we don't know PV bus Q, so.
Right, yes.
Okay. Thank you.
Yeah, that's a good question. Yeah, that's a good question. Yeah, any questions, please ask for the moment.
I have a quick question. So
sure.
For the data sheet, the in the Excel file, the bus data sheet, there's the PGen column. We technically don't use that in the calculations, do we?
Not for this one, no.
Okay.
Not for this one. We'll use that later. We'll use that later. Yeah.
Okay.
We'll eventually use the numbers in that expression, but not yet. Not yet.
Okay, makes sense. Thank you.
Okay.
I've got
I think there was. Yeah, go ahead.
Like pseudo logistical question. At least for me, and I assume a lot of other people, were reading in the data file and constructing our data structure from that. can we but when we turn it in, you said we need to like be able to click run and go.
Yeah.
Are we make any assumptions as to where that file would be when you or the grader, whoever runs it?
We're gonna assume it's in the same folder, right?
The same folder. Okay.
Yeah. So we're gonna assume it's in the. So make sure, yeah, your code runs when they're in the same folder.
Okay, cool. So it's just // wow.
Yeah, yeah. So don't. I guess you just don't hard coding the path, right, from your computer. But as long as they're in the same folder, it's fine. Yeah.
Yep, sounds good.
Yeah. So again, I think many people are struggling with this. It's actually part of the point is to make you struggle with this. So that's part of the point for this homework. So struggle with it, and we will have a standardized code, right? So we'll standardize. If yours works, it works. That's fine. If you can't get it to work, pending something, then after today, we'll give you a version of code that works, right? So the TA will write a version of code that works. So the whole point is to make you struggle through this, because you should at least go through this once, I think. All right. So then after that, we'll use the code to do some other things. But just make sure you do an honest attempt at the code, right? Make sure you do an honest attempt at this homework. You won't actually, the grading won't vary. So you get good grading if you make honest attempt. Good grades if you make honest attempt at the homework. But the point is to struggle through this at least once. Any other questions about homework?
Hey, did I hear you say that we're not supposed to use the P gen column for the PV buses?
Yeah, you should use column B.
Oh,
if
so
you happen not to use column B, switch over to column B. Nothing will change.
That as I guess I assumed that on the PV buses there were also loads, and that like the P and Q that was listed was the load, and then like the generated power was so that like you injected power would be generation minus load. That's kind of the way I treated it, and I'm just wondering if that was wrong.
You can treat it that way. That's fine. If you treat it that way, that's fine.
Okay.
What happens? Treat it that way as your stack bus have a lot of generation. Right, basically you're counting on the slack bus to output everything. In that case, your generator bus actually doesn't do much if you treat it that way. Still, if a program runs, it runs, and from a grading perspective, it's actually okay, right? So we were checking why the program runs.
Right.
If you have time, switch over to subtract the load, to not subtract that. Because that will make your life down the line very difficult. You basically have a slack bus that's outputting, I don't know, like 200 megawatts or something in that homework, right? So if you hard code it, coded that in, it's hard to change, that's fine. But later we'll switch over to, we'll not do that.
Okay.
When we look at line flow, basically if we do that, we look at the line flow, some lines carrying like 200 megawatts coming out of the slack bus, right? So that makes the line flow harder. So just use, if you can switch over, just change the column, change how you read the data.
Okay.
Rerun the program. If already hard coded in, that's fine.
So just so for a PV bus, then the should I treat the P column then as the generation?
Yeah, treat column B as a generation.
Okay,
yeah,
and just basically ignore Q for the.
Yeah, ignore Q. Yeah, ignore
buses.
Q.
Okay.
Yeah. So I think I should have made the file a lot more better. I put in one file because we're going to keep reading that file, so I put every information in that file. What I should have done is I should delete some information that's not useful for this homework. So that's on my that's on me. So that's my fault. I thought it'd be easier to just get one file, not change it. But I think I should have updated the file from every homework. Yeah. Any other questions? Yeah, I think when you're handing the homework, handing your code, just make sure it runs, right? If it runs and output something, we can go through it. If it doesn't run, has an error, that makes it hard, right? Just make sure that something actually runs. Right? So if the output is wrong, that's better than if you're handing something that doesn't run. Good. Okay, other questions? Okay, all right, so let's continue with this lecture. So we're going to look at the generation, and so we're going to look at the basically a bit more interesting case as we have many generators in the system, right? So remember, for a power system, it's not only one generator. We almost never have a system that's one generator connects to one load. I think, I guess for a ship, that's the system you have, one load, one generator. But for power systems, it's never one load, one generator. There's almost many generators, many loads. If you take a graduate level class called power system dynamics, that's really what that class does, is how do I understand this? There's multiple generators and multiple loads all chaining at the same time. And so that's a really interesting problem in power system. And so there's a lot of hard open problems in that setting. And there's a lot of problems we haven't solved. When there's multiple loads, multiple generators, it's always very difficult in that sense setting. So for this class, when we have multiple loads and multiple generators, we're going to treat this as sort of a big generator and a big load. Okay, so this is we're going to treat it. Meaning that if there's imbalance in the load, it's going to seen by all the generators, or changing the generators, sort of spread out in the load. So roughly, even though there's more than one generator, we're going to think of there's only one generator in the load. We're going to treat all this as a single system. Okay, we're going to treat this as a single system. So if you treat this as a single system, then the picture doesn't change very much. Okay, so we're going to assume all the generators contribute together, basically, to the frequency stability of our power system. So that when they all contribute together, then basically we want to look at, so what we have is, right, so steady state. Of all the generation of the generators of the equals to the load. If they're equal, then this means that implies that f, the frequency, is constant. Okay, so the frequency, 60 Hertz, is constant. Then, so if, for example, the total load is bigger than the total generation, then this means that f will decrease. Otherwise, if the load is less than the total generation, this means f will increase. The f will increase. So we're looking at the net power balance, right? So this really doesn't change very much from before. It's just we're looking at the net power balance. Then what happens is, so what you're afraid of is a lot of times is a generator's failure. Okay, so one of the worst fault in the power system that can happen, so one of the things we really worry about when we operate in the system is a generator fault. So if a generator fails, then of course the load will be bigger than the generation. Of course, the load will be bigger than the generation. And this f will decrease. And this is normally a big decrease in f. Okay, this is normally a big decrease in f. So, right, so this basically says that the other generators basically have to catch up. Okay, so the other generators have to compensate. Okay, compensate for the loss of generator. And this is a big event, is because if you look at some things like this, and so whenever you see a big frequency drop, it's basically something of this form. So this is a UK example. Okay, so the nominal is 50 Hertz, right? So this is 50 Hertz because we're looking at a UK system. Okay, so for them, the nominal frequency is 50 Hertz. And if you go along and you look at this kind of frequency drop, this basically is a generator outage. Okay, this is a big outage from the generator. Okay, right? From frequency drops, for example, by 0.5 Hertz, this is a major event. Okay, this is a major event in the system. So if this happens in your system, there's an investigation, basically. So looking at what happened in the system. So it's a big event. Then the system basically recovers. Okay, so this frequency drops very quickly. Then the system recovers through this phase, right? Then the system recovers basically in about 30 seconds or less, in 10 seconds or so. So this is the regulation control. Okay, so this is when they automatically, right? We don't have a human in the loop, so the regulator kicks in and boosts power. Basically, it wants to boost power in the system. Okay, so pushing more power into the system, and then brings the frequency up roughly, you know, by bring the frequency up to 49.8 Hertz. Okay. Then for a long time, nothing happens to this frequency. Okay, then the frequency goes back up. So what happens in this time? Right, the frequency basically, you know, we have fast regulation, so it went up very quickly to 49.8, then sort of stopped, then sort of just, you know, wiggled around for a while. Then a minute later, you know, a few minutes later, then they sort of start ramping again. So what happened in the middle of here? Right, why did it not just completely go back up to 50? Why did it go up, recover, then sort of stop, then recovered again? Okay, so what can cause this sort of behavior? And this is quite common in our system. Basically, what you see is a huge drop, then sort of very fast will recover, then sort of just wiggle around, and then sort of slowly goes back up. So any guesses of what happened here?
My guess would be that the energy stored in the inertia of the generators is causing the slight increase, and then the big recovery is when they actually have the time to like open their gates or whatever their type of prime mover controller is. You know, that delay that you were talking about before finally kicks in and begins to actually increase the speed that they're spinning at again.
Close. So some phenomenon close to that. Basically, there's a 2 time scale. So this part for regulation control, this is basically when you have fast regulation, and we have fast regulator. For example, your gas. Okay, then you can put it happen very quickly. You can sort of change your input energy very quickly. For a coal power plant, it's not going to change in 10 seconds. Okay, so basically, this is when all the fast regulation happen, recovered. Then this sort of, you reach basically a new steady state. Because all the fast things happened, the slow things are you're still waiting for them to kick in. So you recover some frequency, not all the way back, but you run out of room, basically in the fast regulation resources. Right? So your gas generator all kicked on, you know, basically is outputting at their maximum, but you're still waiting for more resources to come in. So you reach this sort of new quasi steady state. You operate for a while, right? For in this case, 3 minutes or so. And then you go up. This is essentially, basically, in this case, a redispatch. Right? This is when humans actually enters in loop and say, okay, so generators, you know, some generators who did not do regulation generate more. Right? This is sort of the human entering in the loop and figure out, hey, I need to change the set point of generator by quite a bit. And then humans kick in and the frequency and go back to 50. Okay, so when the question, is a human in the loop, not for the fast time scale, right? Under a minute, human don't look at it. Okay, so after you wait for, in this case, for 3 minutes or so, humans actually in the control center says, okay, let's do a reduced batch. And then we bring the system frequency sort of back to 50 hertz. So this sort of regulation goes in essentially 2 steps. One is when you have a big drop, recover to some steady state, then wait for the big action to happen, for the reduced batch action to happen. Okay, so this is sort of the way frequency recovery goes, right? So humans in the loop is actually quite slow in this sense, right? So where humans are definitely in the minute, so 5-minute-ish time scale when humans can make a decision. So, right, so it'd be interesting to look at, right, so let's take a, right, so remember, so generator faults are large faults, right? So generator failures are large faults. Okay, so if the system is going to go down, a lot of times a big generator gets knocked offline. Okay. So basically this requires some reserve, okay, reserve. Right, so we need some reserve in the system to protect against generator fault. Failures, okay, we need some reserve. So the question is, how much reserve should we have? Right, so if you're, planning, let's say the next day in the system, you have to protect against generator failures. But what kind of failures do we want to protect against? How much reserve should we have? Should we assume 1 generator can fail, 2 generator can fail? Like how much reserve do we put into the system? So if you're designing the system, how much reserve will you put in? Let's say you get to run the BPA system for Pacific Northwest, and you need to put some reserve. How much reserve do you think you will put in?
1 generator failing, but the largest one?
Right, so the aggressive nature, right, is 1 generator failing. The large generator goes offline. That's for on the aggressive side. But that may be too aggressive, right? So you still want to say, hey, what if you get extremely unlucky and more than 1 generator goes, right? So basically we have aggressive, meaning you want to save money, as to say 1 generator, the largest generator fails. If you go conservatively, you have the largest 2 generator fails. Okay, so, but the problem being conservative is costs a lot of money, right? Reserve basically means I have to get a generator that doesn't do anything, that just is on standby to kick in once a big generator fails. Okay, so normally the people come to a good balance between these 2 requirements. What we do is we say we're going to protect against the largest generator plus half of the second largest. Okay. So a rule of thumb that's using the US is this 1.5 rule. Okay, so the large generator will fail. We're going to assume that half of the second largest generator will fail. We're going to buy this much. We're going to put in this much reserve. Okay, for the system, right? So this is used quite often, and normally this is very close to in practice how much reserve you have in the system. Okay, you figure out the biggest generator, the second largest, and this is 1.5 as you assume will fail. Right, so normally for a lot of systems in the US, this is either a large hydro or a large nuclear. Okay, so for example, in California, this is the 4 gigawatt power plant, the nuclear power plant they have. Right? So that's the plus the second largest one. So this is how you count reserve. Okay. Any question with this sort of reserve counting? Okay, so no questions. Then think about this. So what happens when you have wind? Let's say I build a very large wind farm, 2 gigawatt, which is common. We can build 2 gigawatt wind farms. It's not that hard. So let's say you build a 2 gigawatt wind farm. What does failure mean for your wind farm? Can happen that your wind farm generates no power because there's no wind. Right? So this kind of way of setting reserve. So the $1 million question we have facing system, not $1 million, that's sort of the $1 trillion question we're having power system facing system operator is, what do you do when renewable comes in? Okay, what happens when I have a, let's say I build offshore wind. And let's say offshore in Washington, I build a 10 gigawatt offshore wind farm. What does failure of that farm mean? Right? How do I engineer? How do I think of reserves when I have things like wind and solar that can and often do just generate no power? Okay. If you look at wind farm, for a month, there will be someday in the month that wind farm just generate nothing. Is that a failure? Should I think of that as failure? Should I buy reserve based on that? Like how should people think about when there's a lot of renewables, when the generator is not a discrete? So nowadays when generator fails means it actually fails. So there's something wrong with the generator. You take it offline for a few days, repair it. Wind, that's not the way it works for wind, right? So how do we think about wind and solar or renewables? How do we think about generator failures, generator reserves? Okay. So any suggestions on your side? So this is really the $1 trillion question. Like this will cost $1 trillion because reserves is big money. The reserve market is huge amount of money in reserves. So keeping a generator on standby and not generating power is more expensive than buying power from it because you have to pay the opportunity cost of the generator. Right? So reserves is big money. Part of your bill, like you are paying this money, right? So every one of us is paying money for generators to be on standby as a reserve. So if you have wind and solar, what to do with reserves is a big question. Okay, so that's something to think about. Right? Something to think about. So some of you may work in utilities. You'll be faced with this question. You have to come up with a metric. Some of you work in policy, and as a policymaker, you need to give a guideline, right? You have design policy on this. And so this is quite critical problems. And in the next 10, 20 years, we need to get some sort of policy for this. But right now, we don't have a good idea of, let's say, how do you count wind farms? What does failure mean? How do you count for this sort of stochastic behavior of resources? Now, we still don't have a very good sense how to deal with this. Okay. All right. So, if you're a small system like Hawaii, you can do this through storage. And the solar in Hawaii is not so bad. But if you're a large system like California or PJM, then this becomes a really hard question. Like, it's unlikely we'll have 100 gigawatt of storage in this kind of systems, right? So how do you deal with reserves? A question to think about. A good question to think about. Okay. So I don't have a good solution, but you guys can think about, because if you work in this industry, you'll be the ones who essentially have to deal with this later down the line. Okay, you have to deal with this in some form or another. Okay, so it's worthwhile thinking about now. So any questions about this generator failures, about reserves? Okay, so the rest of the class will look at some examples, I guess, of when things go wrong. We'll look at some example when things go wrong, and what happens when things go wrong. So for basically, we have two types of power system you can think of. There's a large interconnect system and sort of smaller systems. So we have a large system, because large system basically have more inertia, right? Just larger. So the frequency deviation are typically much smaller in a large system. Right? So you basically have, Western US, Eastern US, Europe, China. These are huge systems, and the frequency deviation typically smaller. But also you're more sensitive to frequency deviations. Whereas smaller systems, in Hawaii or some sort of very remote areas, you tend to see larger frequency deviations. Because you don't have that much inertia, you see larger deviations. So how large is the deviation? When do you start to worry about frequency deviation? Depends on the size of the system. But in Hawaii, if its frequency goes off by a hertz, you can probably recover. Now, in the larger system, if your frequency deviates by 1 hertz, there's major problems in your system. Okay? So it depends on the size of the system, the frequency deviation. Okay, so bad things happen, right? Bad things happen. So basically, what happens when the frequency deviates too much, right? So if you think of if there's a large net load increase, either from a generator fault or you just have a large load increase, then basically what happens if the generators are not fast enough, right? So what you worry about at this first dip, if you cannot recover fast enough to bring into this new steady state, then the frequency just keep decreasing, okay, keep decreasing. Then what happens is the frequency drops too low. The generators actually cannot operate at a frequency that's too far away from 60 hertz. Okay, so you cannot have frequency dropping very low and tell the generator, oh, just power through and operate at this new operating point. Our mechanical synchronous generators cannot operate here. So what happens on the generator side is the generator will start to trip offline as a protection system. Okay? Then the last line of defense, or the last thing you do, is you do load shedding. Right? So if the generator cannot catch up fast enough, and there's a net load is too high, you basically have to shed load. Right? You do load shedding. Okay, so load shedding is the worst thing you can do. Right? This is when people lose power. Right? And this is like you really, really do not want to do load shedding. So this is the last thing you do. You only do load shedding to protect against damaging a generator. Okay, so you do load shedding to protect against damaging generators, to protect against even more, to protect against the entire system collapsing. That's when we do load shedding. So there's often a priority list of who should shed load, who should keep load. So if you're, if you go to utility, you'll look at this load shedding. Right? You look at load shedding in this list. Okay, so for example, if you look at the WAC, so this is the Western interconnect. So everything west of Denver. So think of Colorado and west of Colorado. This Western interconnect. Both US and Canada, they're on the same grid. Okay, so this comes in with load shedding. Basically, this says if the frequency ever gets to 59.1, we're going to shed this 5.3% of load. If the frequency drops more and more, we're going to shed more and more load. So we'll progressively shed load if the frequency keeps dropping and the generators are not fast enough to catch up. Okay, so this is quite a bit of load. So if the frequency drops by 2 hertz, we're going to shed 30% of the system. Okay, we're going to start shed load. So if you're in Seattle, do you guys know which is the load we'll shed in Seattle? Like Seattle going to shed load, right? So Seattle power WAC. So let's say frequency drops, we need to choose which load to shed. For Seattle, which is the load we shed? So it's better to drop off this big loads in the system. Right? It's better to drop out big loads in the system, so you don't impact many customers. So do you guys know what is the biggest load in the Seattle system that we have?
Boeing company.
Boeing maybe, but I don't know. So let's say keep within the King County. Yes, I'm actually not sure about Boeing. Let's say within King County. What is the biggest load we have? Not quite too sure about Boeing, but let's say within King County. So when the West Seattle Bridge was still working, if you drive over the bridge, what do you see? If you drive to West Seattle, what is on the left-hand side of that bridge? So stadium is normally not on. So if the stadium is actually, we have a game, we'll share that. Yeah, that stadium. But stadium most times is not a load, right? Most times it's idle.
The steel mill?
Yeah, steel mill. The basically we have a smelter there. So if you drive over the Seattle, West Seattle Bridge, if you south to that bridge, you have this huge smelter. That is the #1 load in King County. That is slightly bigger than UW, actually. UW is #2. So that smelter is #1, slightly bigger than UW. That is, sometimes we'll share that load. If that load has to go, that is about 60 megawatt load. So that's that's a very important load. So you work for City Light, a lot of your time is spending thinking about that one load, right? Because it's such a large load. It comes into a lot of this for stability. Oh, what makes UW #2 is UW just large. UW just large with a lot of buildings, right? And the UW buildings actually consume a lot of power. Right? So if you look at the EE building or the ECE building is actually a very large load. Okay? Even with the reason it's a very large load, it has a very large industrial grade HVAC system. So for a building, a lot of electricity, for example, 60–70% of electricity consumed by a building goes through the HVAC. It's not lighting, it's not any of the load you have. We see in the classroom, it's not the computers in the building, it's the HVAC, it's the air handling system. Okay? So buildings, especially large buildings, consume a lot of power. UW has a lot of large buildings, a lot of old large buildings that's not very efficient, but still have to consume power. So UW is actually, #2 because HVAC systems consume a lot of power. And if you look at all around the world, HVAC systems in buildings consume about 40–50% of the entire electric load in the world goes into HVAC systems. And so that's what makes a campus environment like UW very, very sort of high consumption. Okay? So if you look at so for the folks who have been inside the mechanical building, I'm assuming a lot of you or most of you have been inside the mechanical engineering building. That's a very old building, much older than the ECE building, and it's getting multi-million-dollar makeover. Most of that money goes into the air handling units in the building, right? That's if you're gonna make a building better, the first thing you do is goes down the roof of the building. You make the HVAC system better. So unfortunately, if you go to the mechanical engineering building, it's not gonna look nicer, although the air handling units are gonna be a lot better. So that's what makes UW #2. No, nobody's gonna mess with the windows. They're gonna put in double pane windows for these buildings. Okay, you tell a professor we're gonna put in new windows, you can come to your office for a week. That's never gonna happen. So we're gonna put in new windows. Most of the renovation will go to the mechanical engineering building, you'll see the better air handling. So if you look at the roof of the mechanical engineering building, will be a new roof with new things on it. Inside of it, unfortunately, not gonna change very much. So, and if you go to the ECE building, you go to the 5th floor, there's an attic, there's a lot of air handling units. There's big roof that just have to do with HVAC. So buildings consume a lot of energy. UW is #2. Although UW is not very high on the load shedding list, right? Because it's a campus environment, things like that. But so when we share load, you have a list. So if you're into utility, yeah, I guess utility, if you work inside the City Light, the two things they complain about is that, or not they complain about, the two customers they spend most of their time thinking about is the smelter and the UW. Okay, so any of you work for South Sea Light? No, so it's you'll be on the other side and you still think a lot about the campus. You work for City Line, so you always think about the campus. Okay. So one good example of what happens when a system has a frequency offset is the following. So this is a well-known event in Europe. So November 4th, 2006. And it happened because a ship, basically because one ship was sort of traveling from north to south in Europe. So what happened is this. Okay? So if you look at Europe, basically there's a line. There's sort of a shipping lane going down. So I think going down this way. So this is the important shipping lane. And there's a lot of power lines connecting this way through this lane. Okay, so this is, you basically have a major river, you have a shipping lane, you have power lines connecting over the river, basically. So what happens when you have a ship going over the river? Right? What do you do with the power lines when you have a ship going underneath the power lines? What are you afraid of when you have a power line overhead and you have sort of big ship going underneath it? Okay, so what you do is once you have a ship going under the line, you have to disconnect the line whenever a ship is going under, right? Because you have a high voltage line, you have a big metal ship, with very tall ship, there may be discharge. Okay, you don't want that discharge. So whenever you have a ship going on, you basically have to disconnect the line. To let the ship through. So this is like the bridge. You basically have to open the bridge, right? On Mount Lake, this is what happens. Similar to what happens to Mount Lake. Okay, so when the ship have to go through this, you disconnect the line. So as the ship going down the river, you connect the line, disconnect the line, next one, things like this. So this is a very sort of, you have this coordinated effort when ship going down the line. So what happened this day? The ship says, okay, I want to go through this. And somebody said, okay, let me disconnect the line. What they did not figure out that day was if you didn't disconnect the line, there's actually not enough power flowing from west to east. Right. There was not enough power flowing from east to west. Okay. There's sort of, so you could actually not connect, you cannot disconnect the line because there's a power imbalance if you disconnect the line. Okay, so if you're running this sort of power flow all the time, you should have seen this. But that day for the European grid, for the grid operator, for some reason, they did not take this into account. And the ship says, okay, disconnect the line, let me through. They disconnect the line. And what happened is basically, because there's such big, so there's not enough capacity to power transfer. What happened is every line basically unzipped through this river, across this river. So every line unzipped. This may be Adriatic. This may, I don't know what river exactly this is, but basically everything unzipped. Okay, so because this one line disconnected wrongly, there's not enough capacity. So for protection, the protection on every line tripped. The protection on every line tripped. So Europe basically becomes something like this. If you look at the frequency, okay? You have a low frequency side on the Western Europe because there's not enough power flowing through. You have an over frequency side on the Eastern Europe, and the blue area also is under frequency. So basically you have the three areas. You have the grid divided itself into three areas, and you have frequency issue for all these three areas. So this was a major event. So for example, if you look at the eastern part of the grid, it had a frequency increase, right? So basically frequency suddenly shot up, right? Shot a lot up than 50 hertz. And then they had to basically disconnect some generators to bring this down. Okay, so this is, so the way to handle this is you basically turn off generators. So eventually it recovers to 50 hertz. But the people in, the customers in Eastern Europe did not notice this, because if you trick a big generator offline, still you're serving all the load. So the Eastern Europe part was okay. That's not, people didn't really notice this. The frequency in the Western Europe, this was a bad event. Okay, this was a huge drop here. And this, what happened was the frequency recovered a little bit, then started to go down again. Okay, so it was not enough generation. So here we basically, they had to do load shedding. And this was actually the first time, one of the first times, automatic load shedding was programmed into the system. So the system went to load shedding and was able to recover the frequency back up. Okay, so this was able to recover. But this load shedding happened for 15 million customers. So this 50 million customers basically had to do load shedding. Right, so this was a big event. A lot of people in Spain and Germany lost power because of under frequency load shedding. Okay, so if you look at the country list, basically France lost 5 gigawatt, Germany lost quite a bit, and Austria lost quite a bit. So it's a major event. And this is the sort of thing you try to avoid when we're operating a system. This is the thing we're trying to avoid when operating a system. Right, you don't want France to lose 5 gigawatt of power. Right, this causes significant hardship for people. Right, so this was a sort of really big event. Was studied a lot, and a lot of problems this causes actually for clocks, because when you have a clock, it often uses the electricity, uses the power as a synchronous frequency. So for a while, the clock in Eastern and Western Europe was not synchronized. They're actually a couple minutes apart because the frequency was different. Okay. So we want to avoid this thing. We want to keep these things from happening. But this becomes harder and harder when you have a lot of uncertainty, when you have a lot of renewables. Right? When you have a lot of renewables, you basically sort of stress testing the system all the time. Okay, so the system, this kind of fault doesn't happen very often, right? Disconnecting one line makes Europe divide into 3 different grids. It doesn't happen often. That's sort of a fluke accident that happened. But if you have uncertainties in the system, you have a lot of renewables, you're always stress testing the system, and the chance you're getting unlucky increases, right? You're just testing all the time. So a big part of the thinking about the system engineering power system engineering going forward is thinking about how to prevent this sort of thing from happening, right? Prevent this sort of thing from happening. And how do we engineer a system better? It's actually, again, an open question, but quite an interesting question that people are thinking about. There's a lot of interesting questions. For us, when for this class, I guess you should be aware of these things can happen, right? Why is frequency tied to active power generation? But how do you change it, or how do you engineer a system to be more reliable? As a big research topic, as a big engineering effort that's undergoing right now. Okay. All right, so we'll stop here today. Next Monday, we'll come back. We'll go back to looking at inequality constraints for optimization problems. But otherwise, have a good Thanksgiving, and I will see you next Monday. So this week we'll have a homework, but will be relatively short homework. It'll be a short homework for this week. All right, thanks guys. If no questions, I'll see you next Monday.